Okay, welcome to Chem 652 as we continue our discussion concerning the effects of conjugation. We've covered several things already in this area, but now we continue. I'd like to remind you that there are many effects of conjugation where chemistry is concerned. For example, if we try a hydrohalogenation reaction with a conjugated diene, what we saw was that we can protonate in Markovnikov fashion, but what that does is produce a conjugated or resonance delocalized carbocation. We require two resonance forms in order to describe this system, and because of that we recognize that there are two, not one, but two electrophilic carbons. And our nucleophile can attack either one. We'll call that via path A or via path B. The nucleophile can attack either this carbon bearing positive charge density or this carbon. And so one of the effects of conjugation in a reaction like this is that we actually produce more than one product. Where I've labeled the products that correspond to pathways A and B respectively. There are other chemistries which are also impacted by conjugation. Let's take a look at another one. Another reaction would be halogenation. This is a reaction of alkenes. We know that we can halogenate with molecular halogen, where X is either chlorine or bromine. And when we halogenate, we'll get some product which looks awfully consistent with what we would form with an alkene, where we form an anti-vicinal dihalide, although in this case this carbon-carbon bond is free to rotate, so the anti-nature of the addition pattern will rapidly be lost. But as it turns out, we'll also produce a second product which would look like this. And the question is, how does this come about? This one's more or less the same story that we saw in the previous reaction. We know that as our polarizable halogen molecule approaches the pi bond, the halogen atom that's closest to the pi bond is polarized positive, and it can be attacked by the pi electrons. The relatively weak halogen-halogen single bond can break, and a lone pair on the halogen can bite back down in order to form a species which now should seem somewhat familiar to us because we've seen it so many times, a halonium ion. At the same time, we produce a halide anion. The halide anion can attack, ring open the halonium ion, and we produce the product here. Let's call it product A. That's the one that's consistent, at least structurally consistent, with expectations, consistent with the reaction of a single isolated alkene. But let's take a careful look at this intermediate halonium ion right here. I'm going to redraw it down here. This halonium ion, as it turns out, is formed when we're running a reaction with an isolated alkene because it's a bit more stable than a secondary carbocation. Realize that if this lone pair had not bitten back down to form this halonium ion, that's what we would have, a secondary carbocation. This pi bond would be used to create a 2-electron bond to halogen here, and we'd have a positive charge at the secondary carbon. Well, we can ring open this halonium ion to see exactly what that secondary carbocation looks like in this case. And when we do that, we realize that it's not a secondary carbocation at all. It's a resonance delocalized carbocation. We can draw the alternative resonance form, which would look like this. And so this begs the question, when we have a conjugated diene and we run a halogenation reaction of this type, do we form a halonium ion, when in fact the alternative is to form a resonance delocalized carbocation? It's a great question. In most cases there probably is still some existence of halonium ion, but it's in equilibrium with the resonance delocalized carbocation, as this line would show. As a result, my nucleophile, X-, can once again attack two different spots. If it attacks this carbon, that gives me the same product that I would have produced through a more traditional pathway as elaborated in the line above. But if it attacks this carbon, then I produced this product, which we'll call product B, resulting from path B. So this is another interesting reaction where a conjugated pi system gives rise to more than one product, and we can explain product formation if we understand the effects of conjugation throughout the reaction mechanism. There are other effects of conjugation on chemistry, including chemistries which we already know quite well. For example, we know that SN1 and E1 elimination reactions are both relatively slow compared to a good SN2 or a good E2 because they involve the formation of high energy carbocations. These reactions can become a bit more favorable, however, if, for example, the leaving group is at an allylic carbon. When that leaving group departs, it produces not a primary carbocation, but a resonance delocalized carbocation. This resonance delocalized carbocation is certainly better than your run-of-the-mill tertiary carbocation. It lowers the energy. The carbocation sits at lower energy. The transition state preceding it sits at lower energy, so it's a little bit easier to make, which means simply that the reaction is faster. If I take a careful look at this carbocation, I realize that it is, in fact, a conjugated pi system. Look at this resonance form here. The pi bond in this resonance form implies that there are two electrons, one in each of those p orbitals, and they combine to make that pi bond. But right next door is a positive charge. I know that carbocation is also going to be an sp2 hybridized carbon, which means it'll have a p orbital associated with it, and I have a continuous array of 3 or more carbon atoms, each bearing a 2p orbital. I expect that they would be parallel to one another. They're talking, they're communicating. In other words, these two electrons migrate around this pi system. These two resonance forms say the same thing essentially, but we gain a better understanding of what it means to be conjugated when we think about it this way. Whether or not you show those two electrons there or here between these two p orbitals, as in that resonance form, really doesn't matter. And that's why we say that these two resonance forms are not unique structures, they're just two different pictures of the same molecule. So that's an effect of conjugation. Now if I finish off this SN1, assuming that that's what we're doing, and I think that's what we need to do in this case, if I finish off this SN1 reaction, realizing that in the polar solvent my nucleophilic iodide has drifted out to C, it's been dissociated away from the carbocation. The carbocation is now surrounded by all the solvent water molecules, which are weaker nucleophiles for sure, but this is still a carbocation, and it's still reactive enough to react with a weak nucleophile. I'll generate this oxonium, which can react with another equivalent of water. To give me my final product. So an effect of conjugation in this case is not the formation of more than one product, as we saw in prior cases, but rather the speed of the reaction. This SN1 chemistry is faster because it involves a conjugated allylic cation as an intermediate, a lower energy conjugated allylic cation. So speed is important. That delves into the area of kinetics, the rates of the reaction, and we like faster reactions. They're certainly more convenient than painfully slow reactions. Even the SN2 reaction can be impacted by conjugation. So for example, if I took this iodide, the very same molecule we just looked at, and I attempt to run an SN2 reaction at it, this already looks like a good SN2 substrate because I've got a good leaving group. The leaving group is situated on a primary carbon. All of that screams SN2, especially if I have a really nice nucleophile, and I'm going to go ahead and give myself a nice nucleophile, a cyanide anion. I know that this will approach from the back of the carbon leaving group bond, knocking off the leaving group in concerted fashion to give me my new molecule plus my leaving group anion. So this looks like a standard SN2 reaction, but the truth of the matter is this SN2 reaction is even faster than we might expect. This would be an extremely fast SN2, so the kinetics are again impacted, and oddly enough they're impacted by this pi bond. Now how is that? This reaction doesn't involve carbocations like the prior reactions did, but if we think carefully about the transition state, remember, if we're going to draw a transition state, we show a transition state symbol, which is this double dagger symbol, in the upper right-hand corner outside of brackets. And what we're going to do is we're going to take our cyanide anion and we're going to watch it as it approaches this carbon right here. So it's approaching that carbon. This carbon is at the same time starting to lose its bond to iodine. This bond is lengthening. We're starting to form this bond and break that bond. We've got a delta negative charge on that iodine as it pulls electrons with it. It will eventually be a full negative charge, but at the transition state it's just delta negative. The cyanide anion started out with a full negative charge, but it's starting to lose some of that lone pair electron density as this bond begins to form, so it's now only delta negative. And this carbon atom right here, as we've discussed in the past, at a SN2 transition state, this is actually an sp2 hybridized carbon. And there's the p orbital, which is simultaneously trying to grab onto cyanide while hang on to the iodide. It's a very conflicted carbon. It's going to be trigonal planar. There's a couple of hydrogens on there, which we'll draw in now. And what's interesting is that right next door are two more carbons, and they also have p orbitals on them. They're part of that pi bond. And so at the transition state, I actually have a conjugated pi system. Conjugated pi systems, 3 or more atoms, all sp2 hybridized, all bearing an atomic 2p orbital. It's a conjugated pi system. That lowers the energy of this transition state, making this SN2 reaction all the faster. So if we were looking at a reaction energy diagram, where we plot energy as a function of reaction progress, if this was just a standard SN2 reaction, it might look something like this. But because we've got this transition state, which involves a conjugated pi system, the transition state energy is actually lower. And what that means is that the activation energy is also lower, which in turn means a faster reaction. So the effects of conjugation are really widespread. They show up in a lot of different places, more than we might originally expect. Well, so far we've reviewed the effects of conjugation by looking at reactions we already knew something about. Most recently now the SN2 reaction, before that the SN1 reaction, before that halogenation reaction, and before that hydrohalogenation reaction. Those are all old reactions for us. We utilized all of them in the past, but not necessarily on conjugated pi systems. We're now going to explore a new reaction called the Diels-Alder cycloaddition. This reaction is quite old. It's named for Otto Diels and Kurt Alder, two chemists who worked in the first half of the 20th century. So that would be between 1900 and 1950. They actually discovered this reaction, named after them, in 1928, so a very, very long time ago, almost 100 years ago. Old as this reaction is, it's still one of the very most important reactions, and that's because it produces six-membered rings. So let's look at a Diels-Alder cycloaddition. A Diels-Alder cycloaddition is going to involve a diene, and look, it's a conjugated diene. And it's going to react with a molecule that is interested in the diene, like an alkene or an alkyne. Sometimes there'll be a substituent or two or three or even four on this alkene, but that's a detail. What we're really focused on are the pi systems. So here's a conjugated pi system, and here's a simple alkene. Because the alkene is interested in reacting with the diene, we call it a dienophile. Like a nucleophile is interested in a nucleus or something with positive charge. An electrophile is interested in something with negative charge. A dienophile is interested in a diene. These two are going to come together to form a new six-membered ring. Now, we spent a lot of time in Organic Chemistry 1 talking about the wonders and the beauty of six-membered rings, cyclohexanes and related structures. Cyclohexane itself sits in a chair form in its lowest energy. That chair form has absolutely no angle strain and absolutely no torsional strain associated with it. It's a strain-free molecule, very low energy, and no doubt Mother Nature figured this out a long time ago, and it's why we see so many six-membered rings in nature. Well, this reaction, as I've mentioned, is very important because it forms a six-membered ring. We're going to take that carbon and connect it there, and this carbon and connect it there. We're going to form new bonds right there, and that will make a six-membered ring. So you take your diene and your dienophile, and you can see the six-membered ring that will form even before it does so. The aeroformalism for this reaction is going to involve all the pi electrons. These pi electrons are going to move over here to form this new carbon-carbon bond. If that were the only thing I did, this carbon right here would be in violation of the octet rule. It's already got four bonds, two that are shown, part of this double bond, and then two to hydrogen atoms. This would be a fifth bond. We can't have that. So we're going to have to take these pi electrons and at the same time move them there between those two carbons. But then that creates accumulated diene here, and at this carbon we would be in violation of the octet rule again, because there's a bond to hydrogen which isn't shown. We'd have four bonds plus the bond to hydrogen. That's too many. So we're going to take these pi electrons and kick them over here to form this new bond right there. And all of this happens at the same time, which tells us this is a concerted reaction. That's an important part of the Diels-Alder cycloaddition. It tends to be reversible, at least in many cases, not all. And if we follow the aeroformalism here, this bond, which I'll boldface, and this bond, which I'll boldface, those are the new bonds we just formed. These pi electrons get kicked over there to form a new pi bond right there. Those pi electrons are gone, they're in this new bond. These pi electrons are gone, they're in this new bond. And those pi electrons right there have been kicked over there. So there it is. I formed a cyclohexene. What about my X? My X is still on board. We'll put our X in there. This is our Diels-Alder cycloaddition product, a six-membered ring. Well, the reason we're talking about this now is because it does involve a conjugated diene. This butadiene molecule right here is an example. and it involves the overlap of the pi system associated with that conjugated diene with this alkene. So the way you have to think about these two things coming together to react is not really the way it's shown. They wouldn't sit as flat structures and come together like this, but rather one pi system would be lying on top of the other, and they would come together in this fashion. It's kind of like two pieces of bread that you're going to make a sandwich out of. If you have these two pieces of bread, you don't try to bump them together like this. You put one on top of the other, and they come together in that fashion, and that's exactly what's happening here. One of these would come from the top, one from the bottom. Those pi systems can overlap, forming this new six-membered ring. Again, this is a very important reaction, very special reaction. We're going to spend some time talking about it. But before we talk more about the reaction, I want to talk more about this diene, because when we've drawn 1,3-butadiene in the past, we've drawn it like this. And what I've done in order to get this particular conformation is I've taken this carbon-carbon single bond in the middle and I've rotated it such that now I have this conformation. It turns out that rotation of that carbon-carbon single bond is not quite as easy as most carbon-carbon single bonds, and that is yet another consequence of conjugation. We can understand why. Think about all the p orbitals on this conjugated diene. Presumably each one has one electron, and that's how we get a pi bond there and a pi bond there. But what's to stop us from drawing a pi bond between those two p orbitals, each of which has one electron? And the answer is nothing. There is some pi bond character between those two carbons right there. Even though we draw it like it's a single bond, there's actually some pi bond character. That means there's double bond character there, and we know that if it were a full double bond, we wouldn't be able to rotate that bond at all. If it were a true single bond, it would be very easy to rotate. The reality is it's somewhere in between. It's a little more challenging to rotate that carbon-carbon bond than most carbon-carbon single bonds, but it's not impossible. It rotates with a little bit more energy. Because these two conformations are separated by a larger energy barrier, we give them names. This one is called S-trans, and this one is called S-cis. And the S stands for single bond. So if you look at that single bond, this pi system and this pi system are trans with respect to the single bond, whereas the two pi systems are cis with respect to the single bond here. These are two conformations of the same structure. And as it turns out, in a Diels-Alder cycloaddition, we need the S-cis conformation. We can't get a Diels-Alder cycloaddition to work if we're using the S-trans conformation. We need the S-cis. So that's a little bit of detail about that diene. Let's look at some examples of Diels-Alder cycloadditions. Here is a diene and a dienophile, which happens to also have an aldehyde attached to it. If I want to predict the product that would form from this Diels-Alder cycloaddition, I would draw in my dotted lines, look at my pi systems and how they move about in order to form new bonds, and then draw the corresponding structure. And there it is, a new six-membered ring with an aldehyde on board. Now I mentioned that dienophiles are frequently alkenes, but they can also be alkynes. So let's look at an alkyne. So here's an alkyne. The reaction otherwise proceeds in exactly the same way. I'm going to use one of the pi bonds of the alkyne to produce this new carbon-carbon single bond. I'm going to use these pi electrons to produce a new pi bond there, and these pi electrons to produce the other carbon-carbon sigma or single bond. The difference is I still am going to have one pi bond left over here. So in this case, I still get a six-membered ring, but now there's a pi bond left here, and these methyl groups would be sitting off the edge of the molecule as shown. So these are both Diels-Alder cycloadditions, one which uses an alkene as dienophile, one which uses an alkyne as dienophile. they otherwise have very similar aeroformalisms and behave in essentially the same way. So this is very interesting. Now it turns out that it is possible to make bicyclic compounds using a Diels-Alder cycloaddition. So you may remember that we talked about bridged bicyclics. These are molecules that look like this, a bridged bicyclic. It's going to be possible for us to make a bridged bicyclic in which we have a pi bond present using a Diels-Alder cycloaddition. In fact, I'm going to make that very exactly the same bicyclic with a pi bond exactly as it's shown right now using a Diels-Alder cycloaddition reaction. So I've got a conjugated diene, and look, it's part of a ring compound. It's part of a 5-membered ring, so I would call this a cyclopentadiene. This cyclopentadiene is a little bit different than the butadiene that I'd used up here, but if you look carefully, it has the same exact S-cis conformation that we said is necessary. It has to have an S-cis conformation as it sits inside of a ring, and it looks just like it. In fact, if I were to hide this part of the molecule, those two look exactly the same. So this can be my diene, and for my dienephile I'm just choosing ethylene here just to keep things nice and simple. You want to think about this reaction in exactly the same way. Your diene and your ethylene in this case are going to react with each other, and you're going to form a new 6-membered ring. We can show the aeroformalism just as we did before, and it would look like that. Now, you might be tempted to draw your new product like this, where we have our new 6-membered ring. There's the new pi bond that forms there. And then we've got to figure out, what are we going to do with this? We didn't draw that in yet. Well, that is just connected here and here. So you might be tempted to draw the product in this way, but it's not really the best drawing. It's kind of a bird's eye view of the molecule. If you were flying overhead at 1,000 feet, that might be what the molecule looks like. But we generally prefer to draw these bridged bicyclics from a side view. So if I just take this structure and turn it on its side, what do I have? From a side view, the 6-membered ring would look like this, and this little piece here, which must be coming either out of the plane of the paper or back behind the plane of the paper. I'm going to have it coming out of the plane of the paper. When I turn it on its side, would simply be this piece right here. And so just as I said, that's the exact molecule we talked about earlier. So we can use the Diels-Alder cycloaddition to make bridged bicyclics, provided that we have a diene which is in a ring. Very interesting. What if we use a different sized ring? So how about a 6-membered ring which has the diene built into it, and now we'll react it with an alkyne. Our alkyne is going to be our dienephile. Well, it's getting a little cumbersome to draw the bonds of the new 6-membered ring, but it's going to be between the terminal carbons of your conjugated diene and your dienephile. So I'll kind of just go like this and like that. Pi electrons, pi electrons, pi electrons. Concerted cycloaddition, those pi electrons are all moving at the same time. All the bonds that are being made and broken, they're all being made and broken at the same time. I'm going to once again draw my side view. This is my new 6-membered ring. From here, there, 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 there is here, there, 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 there. New pi bond right there. I started with an alkyne, so I'm going to have a pi bond left over. These bromines are still on board. There they are. And what about these 2 carbons? Well, now this bridge is a 2-carbon bridge up there, and it would look like this. So there would be my bridged bicyclic produced in this particular reaction. Well, are there other types of Diels-Alder cycloadditions? Sure. There are lots of other types. If I go back to an acyclic diene, what would happen if I used something like this. This molecule is known as maleic anhydride. It's actually a very common molecule. It's used for a lot of different reactions. Very useful compound. And it's got this alkene, which can behave as a dienophile. Now, my dienophile is part of a ring. Well, as you can see, when we form our new six-membered ring over here, in this case, I'm not going to make a bridged bicyclic. I'm just going to make a new six-membered ring, which is tethered directly to the five-membered ring that was the maleic anhydride molecule. These pi electrons get kicked over, so I have a new pi bond right there. This is a bicyclic compound, but it's not a bridged bicyclic. This is a fused bicyclic. So it turns out that Diels-Alder cycloaddition is even more versatile than I led you to believe, because you can make bridged bicyclics and fused bicyclics using this reaction. It really is a great reaction, and it finds so much use. Let's go back to bridged bicyclics for a minute, because we need to talk about the fact that if I use a cyclic diene like this one, and I react it with a molecule like this, I will produce my new six-membered ring, and I'm once again showing the side view. There's the one carbon bridge, which is this bridge right here. And now I want to be sure that I include both the bond to hydrogen and the bond to X here. And from the side view, one of them would be up. Let's put the X bond up. And one of them would be down. But I realized that it's possible to draw this in a diastereomeric form, where the bridged bicyclic is identical, but the hydrogen is up and the substituent, in this case a halogen atom, X, is down. These two are different. We see that from this side view. In this case, this halogen is sticking up closer to this one carbon bridge and further away from that developed pi bond. We refer to that structure as exo. This is the exo diastereomer. On the other hand, when the hydrogen is up and the halogen is down, the halogen is now further away from that one carbon bridge, but closer to this developed pi bond. You see the proximity here between X and the developing, now fully developed pi bond. This is endo. So when your substituent is closer to the new pi bond that has developed, we call it endo. When your substituent is further away, pointing well away from it, we call that exo. So we actually make two diastereomers, exo and endo, and you should be able to draw both of them. Now it will turn out that under different circumstances, the exo or the endo might be preferred, might be the major product, but for our purposes, it's safe to say that we're going to produce healthy amounts of both exo and endo product in most reactions where it's possible to do so. So on a predict the product problem, I would expect to see both the exo and the endo product shown. You don't have to label them as exo and endo unless you're specifically asked to do so, but it's important to indicate which is which. The Diels-Alder cycloaddition, such an important reaction. Okay, let's look at one more example. Here I have a much larger ring. It's a seven-membered ring, but I have that conjugated diene in there. That's the key part. And my dienophile in this case is going to be this alkyne. I'm going to make a six-membered ring. And there it is, and there's the new pi bond, which develops when those pi electrons move over there. Because I started with an alkyne, I still have a pi bond over here. And I want you to notice that because I started with an alkyne, this is now an alkene over here, these carbons are sp2. That means they're trigonal planar, and these methyl groups are not up or down, they're now flat. Trigonal planar means that this bond, and this bond would sit in the same plane, and from the side view, this is what it would look like. Let's not forget our 3-carbon bridge. And there would be our bridged bicyclic. So I wanted to point out this example because there is no endo or exo product when you start with an alkyne. Those methyl groups, the substituents on our dienophile, are not pointing up or down, they're flat. That's different than the one we just looked at, where we had an alkene as the dienophile and the X was either up or down. You see we've got 2 substituents off of that alkene carbon, but over here, because it's an alkyne, there's only one substituent. The carbon is sp2, and the 3 groups, or the 3 sigma bonds, are trigonal planar. Here, after reaction, the carbon becomes sp3. It has 4 bonds. That X has got to either be up or down. It's got to either be exo or endo. So that's an important distinction. Well, the Diels-Alder cycloaddition is certainly a very important reaction. One of the most important reactions in organic chemistry. Some people would argue that in the world of synthetic organic chemistry, it is amongst the very most important reactions we have access to, again, because it leads to 6-membered rings. I want to look at a homework problem. Where we're asked to draw the product of this Diels-Alder cycloaddition. This is a cyclic diene. This is a cyclic dienophile. Very interesting. This particular molecule is known as benzoquinone. Either one of these alkenes could be the dienophile. I'm going to choose the one that's pointing in this direction. We're going to form a new 6-membered ring, just as always. Pi electrons there, pi electrons there, pi electrons there. There's the bridged bicyclic part. These 2 carbons right here are those 2 right there, and I realize that they're also attached to the rest of this ring. So, look at this structure. I've got a ring here which is part of this bridged bicyclic, and in this case the ring is pointing up. The other diastereomer that is possible would look identical on this side, but I'll have my hydrogens up and my ring would be pointed down. It'll look like this. Because this ring substituent is further away from the developed pi bond, this one is exo, and closer to the developed pi bond here, this one is endo. So we've got to get used to thinking about these endo-exo structures. They can show up in a lot of different ways. Let me give you one final example of a Diels-Alder cycloaddition. This one's going to involve a very interesting molecule. I'm going to put 3 benzene rings together. This molecule is actually known, so we've got 3 benzene rings fused together, and this molecule is known as anthracene. And it's going to turn out that this part of the molecule, you can see the conjugated diene nature of it, this part of the molecule can react with a dienophile. Now I'm going to keep it simple and just use an ethylene dienophile, but I've got to draw it up above so I can show how it will react. I want to form a new 6-membered ring, which means I'm going to have a connection there and there, so 1, 2, 3, 4, 5, 6. These pi electrons could go there, these could go there, and these down there, and let's see what forms. In this case, I'm going to get a molecule that looks like this. There is the new six-membered ring that formed, and this piece over here is still there, and this piece over here is still there. This is a very exotic looking bridged bicyclic structure in which I have two benzene rings fused to the bicyclic framework. In fact, this molecule anthracene is known to undergo a variety of Diels-Alder cycloaddition reactions just like this. So I think you can see why this is such a special reaction. You can do so much with it. That concludes our discussion of molecules in conjugation or with conjugated pi systems and the effects of conjugation on the chemistry.